Okay. Good afternoon. Welcome to lecture 16 of our computer architecture course. Today, we're going to continue our topic on flash memory and solid state drives. Today, actually, I'm feeling also much better, and I think I'm ready to cover around 350 slides, but we'll see. So yesterday, we were discussing about SSD architecture, and we reached to I/O scheduling part, but that part basically we couldn't finish it. So I'm gonna talk about I/O scheduling very, very quickly and then continue the topics. So essentially, I/O scheduling is one of the parts of FTL in modern SSDs that they are using NVMe protocol. In the past, for SATA SSDs, essentially, we didn't really need to use I/O scheduling inside SSD. We could use basically OS level I/O scheduling. But now, because of these NVMe SSDs that we discussed about, we move all the queues to the SSD. So this is the conventional one. But with NVMe SSDs, basically each process is allocated to a queue, and that queue is allocated inside the storage. And essentially, each process can communicate through that queue using user level codes, such that whenever a process wants to communicate to the storage, it doesn't really need to go through the OS IO block, which can significantly improve the performance. But as a result, we don't really have IO scheduling at the OS level, and it can cause unfairness. And we showed that we have unfairness using these two example applications, TPCC and TPCE. We observed that when we run these two applications together on real SSDs, TPCC actually doesn't really affect much, but TPCE experiences a lot of slowdown. And that's the part that can show that we have unfairness execution across these two applications. So we wanted to see what are the reasons that cause this unfairness. This part basically was the part that we left off. So one of the sources is actually about the IO intensity. We show that basically IO intensity of a flow affects the average queue wait time of flash transactions. So for that, we again use a real system, and we show that when we increase the IO intensity of a flow from 16 megabyte per second to around 1,000 megabyte per second, and this is actually the latency, like the average flash transaction turnaround time. And we are showing the breakdown here, which is like flash operation, which means like that sensing time, that we discussed back then, yesterday. Bus transfer, which is again this DMA transfer latency, and chip queue waiting. And you can see that when we increase the intensity, our queue waiting is actually increasing exponentially. And that can cause basically, a lot of waiting for that. Now things can get interesting when we combine two applications with different intensity. We have one base flow, which we consider as a low intensity, 16 megabyte per second, and interfering flow, which has we can vary IO intensities from low to very high. And you can see that, for example, when these two applications both of them have similar intensity, we don't really observe any, slowdown, and fairness are good. We have one fairness. But as soon as we increase the intensity of that interfering application, we can see that base flow experience a lot of a slowdown. And that can cause unfairness. So we can see this blue curve, like blue plot, which is the unfairness plot. And you can see that unfairness is happening when we increase the intensity. So as a takeaway, when we have two flows and one of them has high intensity, the other one low intensity, the high intensity flow doesn't really affect much when it runs with low intensity. But on the other hand, low intensity flow experiences a lot of slowdown, and that's the source for unfairness execution. Another source is actually chip level parallelism, which we also discussed a little bit yesterday. Like imagine there is one flow, which we showed here with blue, and this doesn't really provide good chip level parallelism. It actually that's what the definition of chip level parallelism. So we want to distribute across chip level queues, but now we have two applications, and one of the flows doesn't really provide good chip level parallelism. Like 3 requests are going to the same chip and one to another. And when another request, another flow, which like the blue flow that has good chip level parallelism comes here, you can see that even though, remember that HIL, the host interface layer, can send the acknowledgement to the process, to the host system when all the requests are ready. So for blue, actually, we could have done it completely, you know, for only as the latency of 1 request, you know, because it's completely parallel. But because of the red flow here, this blue request also needs to wait a lot. And that's the reason. Like basically, we can say that blue request is experiencing a lot of slowdown because of the red flow. So red flow doesn't really you know, experience much because it has that problem. Like it doesn't really have good chip level parallelism. But blue one has. But unfortunately, blue one also cannot benefit from chip level parallelism because of the red flow that we have here. So it's another source, and we show it with some results as well. Another source is actually about prioritization that is happening for reads. We also briefly discussed it yesterday, that we usually want to prioritize reads over writes, and that can provide some basically performance. But the problem is that we cannot prioritize reads all the time over writes. So we show that with some experiment here. So there is an application here. Some of these actually experiments are with simulator, some of them with real. This one actually, I guess it's with simulator, if I'm not mistaken. But anyway, you can read the paper for that. So we have 4 different base flows here, you can see, and each of them has different write ratio. Like when we have 100% write ratio in base flow, which is the black plot here, it means that there is no basically read request for that base flow. And we have also the interfering flow that we increase like the read ratio. So with interfering flow, when it has 100%, meaning that all the requests are reads. And you can see that at some point, like this is fairness improvement. At some point, actually, we are reducing fairness if we prioritize reads over writes all the time, especially when the interfering application has, you know, all the time has reads. And also the base flow has writes all the time. So you are observing much more basically reduction in fairness. So this is also interesting. So your scheduler needs to be smart enough, intelligent enough to understand that until what certain point we can prioritize reads over writes. And another source is actually like garbage collection demands. Like when we have different applications or different flows running together, some of them are write intensive, essentially. They have issue a lot of writes. And because of those writes, they also issue or invoke, or basically they cause invocation of garbage collection. And that garbage collection can be treated as noisy neighbor, actually. So basically that application that has a lot of writes can be considered as a noisy neighbor for another application that has only reads. So again, this also effect of garbage collection can, you know, cause a lot of unfairness for the application that doesn't really issue garbage collection. You can check the paper for more detail, but I gave you the overall idea about it. So as a summary, these are the 4 major sources of unfairness that we have observed, like different I/O intensity, request access patterns, read-write ratio, and garbage collection demands, essentially. And to overcome that, we designed FLIN, flash level interference away SSD scheduler. So FLIN has 3 stages, basically for I/O request scheduler. It replaces existing transaction scheduling unit. So this part that we already have. So there is this transaction scheduling unit in the baseline, but that doesn't really consider any fairness things. So we just replace FLIN with that. Sorry, we replace TSU with FLIN. And it takes in flash transaction, reorders them, and sends them to flash channel. So we observe that it has identical throughput to a state-of-the-art schedulers and fully implemented in the SSD controller framework, because there is no hardware modification and it requires less than basically 0.06% of DRAM available within the SSD. So it doesn't really need a lot of metadata. essentially. So FLIN has 3 stages. In the first stage, actually, is because of that different IO intensity or access pattern. So basically, the first stage tries to address the 2 sources of unfairness that we discussed. So you have this queue of the request, and this is the tail, and this is the head. And we try to order them from high-intensity flows to low-intensity flows. When we receive a request which belongs to low-intensity flows, we just insert it in the head of basically queue. We don't just, naively put that at the end of the queue, essentially. So we try to, do some insertion policy here. And that can also be reordered if needed also. Another step of FLIN is actually priority-aware queue arbitration. Like that enforces priority levels that are assigned to each flow by the host. We didn't discuss about it, but that's actually part of NVMe protocol. In NVMe protocol, if a process needs more priority, basically it can, communicate that or convey that to the SSD essentially. So there should be some basically scheduling technique that also consider that different flows can have different priorities. So stage 2 actually is for that, to enforce priority levels that are assigned to each flow by the host. And for stage 3, we do weight balancing transaction selection. This is actually for relieves read-write ratio and garbage collection demand interference. Essentially, we try to estimate or calculate how much, basically how much time we wait for each write request. So at some point, the amount of time that are waiting for one write request to schedule or to execute can actually exceed the write program latency. The write program latency is around, for example, 700 microseconds. But if you wait for that write request to be scheduled for, let's say, 1 millisecond, then you can see that you are now, you can cause unfairness to that write request. So for more detail of these steps, you can actually check the paper, but I just want to conclude with some results. We use a MQSim, actually the simulator that we have developed together with this work. We wanted to do research on this topic of NVMe SSDs, and because NVMe SSDs, they are considered as multi-queue SSDs, that essentially each application has a queue. So, but back then there were no actually SSDs, simulator that can simulate that. So we develop our own simulator with much, a lot of different also characteristics, including these multi-queue SSDs. And we publish MQSim in FAST conference. And so we will also discuss MQSim in one of the lectures as well. But you can check MQSim from this GitHub page. We also test different workloads, and we group them like containing 4 randomly selected storage traces. We try to make mixes of workloads essentially. We also compare against different baseline schedulers that we can check. But essentially, FLIN provides quite good fairness compared to prior work. So FLIN improves fairness by an average of 70% by mitigating all 4 major sources of interference. And also the weighted speed up, FLIN provides better performance. So FLIN is not only fair, but also high performance. And that's the key, that sometimes providing a fair solution should not be really also, necessarily should not be conflicting by high performance solution. So that was the very important insight that we got from this work. There are many other results in the paper that you can check, but that's about it, like the FLIN. Any question? Of course, I didn't provide a lot of details here, but you can check the paper. But I think you got the overall idea of this work. Now the question is, what is next? Do we need something on top of FLIN? Any thoughts? People actually have looked into more, let's say, fine-grained controlling. So in FLIN, actually, we try to have a kind of binary categorization, like low intensity, high intensity. But people also have looked into designing some fuzzy control unit that can actually, even basically differentiate across low intensity workloads, high intensity workloads. Of course, that can provide better results at the price of more cost, basically. And then it's a solution, like that's a question again. You have a trade-off here and you should see if it's worth it, essentially. But that being said, I think there should be a lot of work still on this area. And we are also looking for interesting, like excited students to continue this line of research. Okay, another important topic is flash memory array parallelism. This work, Venice, that Rakesh and we call it together, is about providing, like improving SSD parallelism at low cost via conflict-free accesses. So I will give you high-level motivation very, very quickly. This is the background of SSD that you already know. But this part, maybe you don't know much. So flash chips are connected to the flash controller using shared channels. And you can see that essentially, sometimes your requests are accessing different flash chips, so they don't have conflict. I mean, they shouldn't have conflict because they are going to different flash chips. But unfortunately, these flash chips are sharing the same channel. So even though they are targeting different flash chips, they need to be serialized because of that. And that can cause conflicts. And we showed that we named it as a path conflict. And we showed how this can cause performance overhead. Like you are receiving 2 requests that they want to go to different flash chips, but unfortunately they have path conflict. Like you send the commands in a serial manner, and then you need to send you can do the read operation. This part can be overlap a little bit. And then we have data transfer. And then you can see that for this flash chip 1 needs to wait for flash chip 0 to be done with data transfer such that it can start issuing that. And that can cause basically a lot of latency. Well, if we can actually send our requests to different channels, clearly you can do everything in parallel. And that's the saved cycle that you can get. So we did some experiments. And we observed that path conflicts increase the average I/O latency by 57% in our experiment on a performance-optimized SSDs. And the performance overhead of path conflicts increases by 1.6 times in our experiment for high I/O intensity workloads. Yes. Yes. Yeah, exactly. I mean, we do have access, but I think this experiment, we didn't use real SSDs, right? Yeah. Yeah, I mean, using real SSDs for every experiment is, if possible, is good. But at the same time, you should also consider sometimes, the time, if you can make your point with something with the simulator. We're going to actually have a lecture on simulation, and that's we go into deep about why simulation makes sense, why sometimes modeling makes sense, sometimes prototyping makes sense. So I think that lecture is also going to be exciting. So there has been some prior work that they want to address this problem. So this is the baseline SSD. There has been one work like packetized SSD. I'm not going into detail of that, but essentially what they have done here is that we have some I/O pins for each flash chip, and also we have some pins for control. And together with all these pins, you can have 16 pins, essentially. So in this work, they consider that they can move a part of control, like the part of control which is usually in the flash controller. They add that control unit inside the flash chip. So that comes with at the price of overhead, essentially. But then now they can use 16 pins for sending a request. So essentially, they have the twice the wider shared channel, and that provide like higher bandwidth, essentially. But the issue is that baseline SSD and packetized SSD, both of them do not provide path diversity to flash chips. And that was actually our main point here. In order to avoid path conflicts, you need to fundamentally provide path diversity. This design, yes, it mitigates the overhead, but still you don't have path diversity. And essentially you can have path conflicts again. So that being said, there are some works like this, again, packetized network SSD, which is actually another technique proposed in the previous paper. So they discussed adding some horizontal channel and also vertical channel. And now you can see that, oh, okay, now we have some path diversity and then we can reduce the number of path conflicts. But yeah, based on our experiment, that doesn't really help much because it only increases path diversity by 2, which is not enough. Another work is also network on SSD, has been proposed in Cal 2012. This actually provides a rich path diversity, but we observe that it has quite basically large area and cost overheads, and also do not effectively utilize the path diversity. So now you have path diversity, your infrastructure provides that, but then your controller needs to be intelligent enough to use this path diversity in order to avoid conflicts. And that's essentially important. So that brings us to our goal that we wanted to fundamentally address path conflicts problem in SSD by increasing the number of paths, like providing path diversity, and effectively utilizing the increased path diversity for communication. That being said, we reached to Venice. We thought that Venice actually has a very good connectivity. I'm not sure if anyone visited Venice. Okay. So it looks like they have a lot of canals, but I can see also they have a like quite shared channel, you know, here. So yeah, not sure actually is a good naming or no, but Rakesh didn't like it actually. And it's interesting that we changed the name of this paper just 1 hour before 30 minutes before the submission. Like the submission was, I don't know, around 12 p.m. Yeah, Rakesh remembers because it was painful for him. So just 30 minutes before the deadline, we decided to change the name, and he had to change all the figures, all the plots, you know, because when we have different mechanisms, one of them is Venice, and it has the previous name, so he had to recompile and everything, you know, regenerate all the PDFs. And it's amazing that we didn't make a mistake. Okay. So Venice, a low-cost interconnection network of flash chips in the SSD and conflict-free path reservation for each I request, and non-minimal fully adaptive routing algorithm for path identification. Let's quickly take a look at Venice. So our key idea in order to reduce the overhead is that we devise a new topic, let's say, terminology like flash node. And each flash node consists of one flash chip and a router chip, essentially. And flash, so that being said, basically router chip is connected to flash chip still with 8 IO pins. So one of the reasons that prior work network on SSD is actually quite costly is that flash chips are in the network, which means that this flash chip, this poor flash chip needs to have like 32 bits, 32 IO pins, which is not possible, right? So this paper actually consider, when this paper wanted to compare against this one, consider that, okay, yeah, this one is 4 links, 4 injection, let's say, input. So now I'm going to consider that each link is only 2 bits, essentially, right? And they show that, oh, we can beat this baseline. And that's true. I agree. But the thing is that you can actually make a better design by considering that, okay, I have a router. Routers are in the network. You know, we have 4, but router is connected to flash chips with 8 IO pins. And that's the key reason that we reduce the cost here. Links are also bidirectional link, meaning that we use the same 8 pins, 8 wires essentially for 2 direction. That also can reduce cost. And yeah, so that's, as a result, Venice provides increased path diversity at low cost. And we don't have any modification to existing flash chips in Venice, which is very important. Because when you think about SSD actually is a system design, and they design it on a system on board, essentially, you know. But flash chip is a chip which is like, you know, fabricated from flash companies. And it's not really easy to change flash chip architecture, but you can actually think of changing SSD because SSD is a system design, and you can, you know, design it differently, essentially. Do you agree, Rakesh? Yes. How do you estimate it? Yeah, that part was actually a bit very hard, to be honest. But what we have done. So for router chip, we basically synthesize it with the, this synthesizing tool, I guess, Synopsys design compiler. And we calculate estimated the area for the die. But that die area was actually quite small because our router is quite small and it's very simple. But the problem is that the overhead of router chip, like the area of router chip, is dominated by the I/O pins, essentially. Even though the die is quite small, when you want to package it, you need to spend a lot of time. So we went actually through all the different standards related to the distance between I/O pins, like the I/O pads, how big they should be, depending on the frequency, depending on the resistance of that wire. I mean, we have done really a lot of, we did our best, honestly. But of course, it's not really possible to do it very accurate, but we did our best. And then we essentially consider that, okay, here, for example, we need 8 I/O pins, and between each I/O pin needs to have this like wide, and then the distance between 2 wires should be that. And with that, essentially, we consider that, okay, what is the X and what is Y here? And we calculate the area of that router chip. And that's... So in this, the technique can be actually different, right? It can be applied to different baselines, but I guess in our experiment, we consider 8 times 8, right? 8 times 8, basically, architecture. And that's the area for router chip. We also try to estimate the area for wires here. This is actually quite interesting, even though we add many links here, but that actually reduces the area of wiring. Because once you have a shared channel is actually quite long, right? And since it's quite long, in order to provide good performance, you need to make it wide, such that you can have a good, enough current. So with these links, they are short. So making them high frequency, you don't need that wide. So you can actually, make them smaller, like thinner, let's say. And that can reduce the area. So in the end, we report in our paper that, maybe I have some slide for that, we'll see. We reduce the area for this and we increase the area for that. So in the end, we don't know. People should see. Okay, so this is actually one of the interesting parts of this work, conflict-free path reservation. So once we want to create we need to reserve a path, essentially, from flash controller to the target flash node. Assuming now we have a target flash node F8, we send a scout packet from flash controller. Each scout packet actually, when travels through the routers, try to pass through this crossbar and then reserve a path. Basically, that router put the note here that this scout packet actually traverses from this output. So we need that because we want to reserve a path and reuse this path. We're going to also have a lecture on interconnect, and you're going to learn about interconnection network terminology a lot. But I think crossbar is not something so, I guess, strange for you, right? It's just, you can consider a crossbar as a several multiplexer, essentially. Yeah, this is also router reservation table that we say, we keep the entry port and exit port, and also if it is valid or not. Okay, now the scout packet, when it arrives to flash 8, it returns back to the flash controller. And now flash controller realizes that, that the path is established. And we can use this path to send our request, essentially. Okay, later on, we have another target flash node. And that's the key difference here. Since we have a network, we can actually assign flash controller 2, for example, here, and send a scout packet and make another reserve path here. And that's how we are benefiting from path diversity. We also put one step forward, and we use non-minimal fully adaptive routing in order to do that. So now you can see that we are trying to reserve a lot of paths here to F8, this one to F6, you can see, and this one to F7. Now you want to reserve a path to F2, right? And you can see that there is no minimal pass actually that can be, that can reach to F2 without any conflict. But you can actually use a non-minimal pass, like this, to reach to this F2. And that's a very important part of Venice mechanism, that we use non-minimal pass in order to avoid conflicts. There are a lot of interesting results in the paper. You can check. Again, we use MQSIM, and we had two SSD configuration: performance optimized and cost optimized. This Samsung NAND SSD is actually one of the SSD which is like, they are performance optimized. They use smaller pages, like 2 kilobyte, 4 kilobyte, as we also discussed yesterday. We also use different data intensive workloads and a lot of baselines. Yes.
It makes sense to try other network.
Yeah, it makes sense. We did we do that actually? Yeah. Yeah, so mesh topology is actually quite simple. Throws, because of this wraparound, like long wraparound is not that simple. But the problem also, another point that you should consider here is that we show that the bottleneck is not the diameter of the network. Actually, you can actually use a network with a long diameter because your packets are quite large. Like they are like 16 kilobyte of data, right? And you're gonna have your packet for a long time because your links are also quite small, narrow, like 8 bits, essentially. So in the end, basically your latency is bottlenecked by the packet size. If you have a long diameter, yes, it will take some time for the first 8 bit to reach to the destination, but then it's just every cycle have another 8 bit because it's a pipeline, right? Exactly. So yeah, we made also that decision. But again, that can be also interesting to see how different topology. There are also other topology like indirect topologies, like butterfly, for example, flattened butterfly that we could consider. But yeah, that part we can check. Yeah, once it is reserved, another request cannot use that.
So then, say another request comes in.
Yes. Yeah. So the idea is that you reserve a path such that you don't need buffers. So our routers are quite simple because they don't have buffers. The other way around, you need buffers like 16 kilobyte or whatever, so it's just huge, right? Those were really good questions. Okay, so yeah, as expected, Venice is great. Oh yeah, this is also interesting here. We have a pass conflict-free SSD, which ideally we consider that we have, like when we have 64 flash chips, we consider that ideally we have 64 channels, right? Meaning that, yeah, there is no conflict anymore. And you can see that Venice actually bridged the gap quite well. These are also results for cost optimized SSD. You can see that we are actually much closer to the ideal SSD. And this is also quite interesting that we showed, yeah, reduction in pass conflict. Basically here is the baseline SSD and other baselines, how they reduce pass conflicts. And with Venice, you can see that pass conflicts are quite low, essentially. And yeah, 99.98% of IO requests do not experience pass conflicts anymore. We also evaluate energy consumption that you can check. Venice provides better results. Yeah, we also studied area overhead, which you can also read the paper for that. Okay, so yeah, that's about Venice. That Venice provides good performance and energy consumption by providing path diversity for flash array, and that can reduce path conflicts essentially. Question? Okay, let's see. Yeah, every time I check the time, I'm scared. But it's good. Okay, we are done with the agenda of our previous lecture. Now we want to have a deep dive into flash memory study. And this paper is like the modern survey on flash memory that we published in 2017. There is also a more up-to-date version in 2018. That if you want to learn a lot about flash memory reliability issues, what are the techniques to to overcome these reliability issues, you can check this paper, and this is quite interesting. So here there is a short background on flash memory, which I'm not going to cover because you know most of them. I'm going to wait on some specific slides because I want to point out some important thing. But essentially, you know about these row and like the column, floating gates, all these stuff are known to you. You know that we apply VPass to other word lines when we want to access flash, and you read. This is also a side note here that we usually consider NAND flash memory because NANDs are like capacity optimized and like cost optimized. But on the other hand, we also have NOR flash memory, which NOR flash memory provides better connectivity. You can see that the connection to the bit line, we have more parallelism essentially here. NOR provides better performance, but at the cost of more connectivity, which that's the reason that NOR is not being used, at least for SSD devices. There might be some devices that they use NOR flash memory, but I'm not sure. Rakesh, do you have any idea? It become very rare, yeah. Okay, so yeah, these are multi-level set that and the threshold voltage reduces over time that about it as well. And once it reduces, if you want to keep your reference voltage as before, you're going to have a lot of errors. So the idea is that now you need to come up with the optimum voltage, like the reference voltage, that still will cause some errors, but then you can have minimal raw bit errors. And you can hope for correction of them using ECC. So always the idea in flash memory is that at some point you're going to get some errors, but you need to try to optimize your decisions in order to have the errors less than the correction capability, like the maximum capability of your ECC, such that you can correct errors. And the way that we usually program MLC is that from the arrays, we go to the LSB program that we only program the LSB. It's kind of like a big endian here is considered. So for arrays, you don't do anything, but when you want to program the LSB to 0, you just go to this temporary state. And then you can, from this arrays, you can increase threshold to go to P1. And from the temp, you can increase to P2 or P3. This is considered as the two-step programming that we have for MLC. But beyond that, also, we have this ISPP that we already discussed, that for each of them, we also need to do this incremental set pulse programming. Okay, and in MLC architecture, you can check the paper for that, but essentially you distribute pages through different cells in the flash memory. Okay, now we get to this part of background which I like to focus more. So we discuss today a lot about planar NAND flash memory, which is like the 2D NAND. And then in the end of this lecture, hopefully if we get to that, we're going to see also about 3D NAND flash memory a little bit. The thing is that in planar NAND flash memory, vendors, in order to provide better capacity, they had to scale it down. So they had to scale down, go to very low scaling. And that makes flash memory smaller and smaller, and you can guess the issues, essentially. The whole issues that we have also with DRAM, with the DRAM scaling, we also had that with flash memory. But fortunately, they came up with the idea of 3D NAND flash memory, and now they have another degree of freedom in order to provide capacity. So they could actually make cell a bit larger, such that they don't have that much errors. But then they build cells on top of each other, like in 3D layers. So with that, they provide both capacity and also better reliability. So 3D NAND flash memory actually acts as a breeze, I would say, for the vendors. So vendors could actually, breeze a little bit for that. But now also, after some time, for 3D NAND flash memory, they also need to, because we always want higher capacity. So now they are also reducing the cell size for 3D NAND flash memory, and we are getting into issues that we had before with planar. So it was just, like a temporary breeze for the manufacturers, but now still they have problems. This is a structure for 3D NAND flash memory that you have different layers, and you can see that the bit line actually goes across the layers. Word line is still per layer. So each word line goes through the layer, but block is actually basically distributed across layers. So this is complete. This one is a block, for example. And this is a cross section of a charge trap transistor. It's a design of that you have this control gate, which is wrapped around this flash cell, and you have this gate oxide, and this part is a charge trap, which is like the insulator. So yeah, that's what basically the function of that is not that much different compared to floating gate. But it turns out that so floating gate can be also built for 3D NAND flash memory as well. But it turns out that using charge trap is easier to manufacture for 3D. And that's why that's the common technology for making 3D NAND flash memory. Okay, so now let's look into some flash memory reliability and security analysis that we have done. So this is a slide that you know a lot about it, that these two memories like DRAM and flash, both of them have issue. Reliable sensing becomes difficult as charge storage unit size reduces. So the problem that we focus here in the whole study that I'm going to discuss now is that MLC NAND flash memory reliability and endurance is a key challenge for satisfying future storage systems requirements. And our goals are twofold. First, build reliable error models for NAND flash memory via experimental characterization, and then develop efficient techniques to improve reliability and endurance. It's very similar to what we also have done for DRAM. With our infrastructure, we learned about issues, and we try to predict things, like, for example, with the retention aware control, like the refresh control. And then, so once you know the source of errors, and once you know how you can model them, then you can develop efficient techniques to improve reliability and endurance, as well as also performance. So this lecture is going to provide a flash summary of our recent results published. It's not that recent, actually, but in the past 10 years, essentially. So these are some of the papers that I'm going to discuss today. So yeah, in this figure, you can see the evolution of NAND flash memory that from the time that it has been manufactured more and more. Basically, people can make SLC NAND flash memory with higher density, MLC as well. And the idea is that can we scale it more and more? But that will come to, because it comes at the price of a lot of issues. So first of all, like the P cycle provided is few thousand for MLC NAND flash memory, for example. But the P cycles, which is required by the standard stack here, is like 10 times per day for 5 years. That's the endurance that you need to provide based on some standard, essentially. And that means you need to provide something around 50K P cycles, essentially, which you can see that we are far away from that. And this is also, you can see that decreasing endurance with flash scaling, as we also showed, and also with using MLC and TLC. Here we don't have TLC, but essentially your endurance is reducing when you use lower technology node, and also when you use MLC as opposed to SLC. And in order to provide reasonable lifetime, you need to actually add more ECC. You need to make your ECC more like powerful, essentially, to have reasonable lifetime, essentially. So endurance of flash memory decreasing with the scaling and multi-level cells, and error correction capability required to guarantee storage class reliability, which is uncorrectable bit error rate. This is actually the metric that we also have for HDDs. So once you have this uncorrectable bit error rate less than 10 to the power minus 15, then your device is considered as reliable, essentially. So then we need more ECC in order to obey this standard, essentially. So you can actually treat NAND flash memory as a noisy NAND, like the noisy channel that you write it and you read noisy from it, essentially. It's very similar to a noisy channel, right? That you talk to that channel and that channel has a lot of noise and then you cannot get your data well. So we know that our NAND flash chips are noisy. So we do some memory signal processing and we get raw bit error rate, which is unfortunately high in like the traditional techniques. And then we need to apply expensive error correction in order to get this uncorrectable bit error rate less than 10 to the power minus 15. So our idea in this work, in all these works that I'm going to discuss, is actually to get lower bit error rate such that we can get simpler error correction. And then hopefully we can have better results. So we want to build reliable error models for NAND flash memory to design efficient reliability mechanisms based on the model. And that can, provide a better lifetime within the, basically, within the same error correction capability. Yeah, so in order to do that, you need to actually work on the different parts of this noisy channel. You need to work at the right, like the erase block and program page. These two operations actually cause some reliability issues that we're going to show. And then we also have this neighbor page programming and read interference. You can consider it similar to RowHammer. But yeah, this also is a little bit, actually, the function is different, but we're going to see. So you need to also work on it. And then we have retention error, which you also need to work on it. And hopefully, if you address all of them, you can actually make this noisy channel much better. So I'm not going to repeat this. So you know that the goal is to understand error mechanisms and develop reliable predictive models and develop efficient error management techniques. Our approach is basically solid experimental analysis of errors in real MLC NAND flash memory. And with that, we want to derive the understanding and models. Here are some basically list of different types of errors mitigated by NAND flash error mitigation technique. These are different papers, references, different like error type and how people have overcome it. It's actually a very nice survey. So if you want to read about it, you can check this paper to get a lot of good information about it. Okay, this is the experimental testing platform that we used. We've been working with some industry back then, and they helped us to to make this infrastructure, and we could handle every NAND flash memory nicely, to control the data. But it's actually very. I'm not saying it's completely similar, but the idea is similar to DRAM Bender, for example, that we are using for our DRAM studies. Okay, so in NAND flash memory, we have 4 types of errors based on the paper. This paper, it's actually one of the first paper I read. It's actually quite interesting for me. It's one of the first paper I read from Professor Mutlu. Back then, I was still like around bachelor, and I was reading about emerging memory technologies, and I wanted to learn more about flash memory. So my advisor suggested this paper to me, and I read it. And it's very interesting that I'm now also presenting this paper after how many years? Like 13 years or 12 years. Okay, so there are these error types. So we have read errors, erase errors, and program interference errors. We're going to learn about all of them. And there are also some errors that are caused by flash cell losing charge over time, which we call them retention errors. It's very similar to retention error in DRAM, but it's not that frequent or that fast compared to DRAM. Okay, so the thing is that this error model is actually quite complicated. If you want to have a nice model, you need to design them because you have errors in raise block, you have error in program. When you want to program your page, you have errors. You have retention errors after some times. And then when you want to read, you have read errors. And once you have more days, your retention model needs to be, again, different. So you have more retention errors, and then you need also have a read error. So you can see that you need to work on all these different domains in order to have a holistic model. Okay, so in our methodology, we characterize errors and error rates of these two technology of MLC NAND flash using an experimental FPGA-based platform that I showed. And we quantify the raw bit error rate at a given P cycle. So this raw bit error rate is actually the error rate before ECC. So once you have this raw bit error rate, but you hope that your ECC is strong enough in order to make your raw bit error rate to less than uncorrectable error rate, which should be less than 10 to the power minus 15. But the problem is that at some point, your raw bit error rate is basically is greater than the capability of your ECC, and then your device is dead. So our idea is that we want to reduce raw bit error rate as much as possible, such that you can continue using your device within that ECC capability that you have. Okay, and we want to quantify error correction capability and area and power consumption on various BCH code. BCH code is actually one of the famous code used for flash memory, which stands for the first, I guess, surname of the three scientists that they have developed this code. You can search for that. I don't remember actually their names. Any of you know? You can also search right now. But anyway. But yeah, mostly this lecture is going to talk about characterized errors that we have done and also quantify raw bit error rate at a given P cycle. Okay. Before jump into the topic, let's have break for 13 minutes, and we will get back at 2:20. Unless there are some questions.
你这不是既有那个，不是你上面的四张图不是既有 operation 又有 那我就很无所谓啊。只要人花时间做这两种，对吧？
Am I audible? Am I audible? Okay, let's continue. We still have 200 slides to cover. Okay, let's see some main characterization results. So we have tested different error types and like testing methodology. Erase errors, we count the number of cells that fail to be erased to 1-1 state. So when you want to erase, you want to get to this state, essentially 1-1, right? And we count the number of cells that they couldn't reach to this state, essentially. For program interference errors, and our methodology was to compare the data immediately after page programming and the data after the whole block being programmed. So yeah, once the data, once you program a page, you capture that data, and also after the whole block being programmed, meaning that you had a lot of program in that block, and all these program can cause program interference. So if you check the initial state and the final state, you can see some issues, essentially. For read errors, we continuously read a given block and compare the data between consecutive read sequences. And for retention errors, we compare the data read after an amount of time to data written. We characterize short-term retention errors under room temperature. And for long-term retention errors, like 1 year or so, we use this methodology in order to accelerate retention time, which you bake essentially your flash chips in the oven at the temperature of 125. That's actually, that has been proposed for some other, let's say, devices. I don't remember actually the name. They are not, I think they are not reported for flash memory. But it's a kind of a process that people have developed in order to accelerate aging, essentially. So they bake their devices in the oven. But this work also, you know, we thought that, okay, we can do this similar stuff for flash chips, and we have done. And later on also, people have also developed techniques, you know, on top of this baking stuff. So this is a known technique. Okay, so this is our observations for flash error analysis. You can see that we have different plots here, like errors for retention errors for after 3 years, retention errors after 1 year, 3 months, and 3 weeks, and 3 days. And there are also some other errors like program interference errors, one day retention errors as well, read errors, and erase errors. And essentially, like the takeaway message here is that raw bit error rate increases exponentially with PE cycles. So once you have more PE cycles, you can see that you have more errors. Note that this y-axis is actually logarithmic. So that's why you are seeing like the linear line, but essentially it's exponential. And retention errors are dominant. So more than 99% of errors for 1 year retention time is actually allocated to retention errors. And the retention errors increase with retention time requirements, of course. So that's the thing, you know, if you want to start with flash memory and fix a problem, better to start and fix the retention errors. But once you fix retention errors, you can see that other errors can be now a bottleneck, like the program interference errors, read errors, and erase errors. So for retention error mechanism, you can see that so essentially you move through this window of threshold voltage. And we make some interesting observation that cells with more program electrons suffer more from retention errors. Like this, this state that we have more electrons because we need to have a higher threshold voltage, it actually moves, it moves a lot more than other. And it's very unlikely that they move more than 2 windows, basically. So they usually, threshold voltage is more likely to shift by 1 window than by multiple. So these are also our observations. Here also you can see more results, like more detailed results, like going from state of 0, 0 to 0, 1, 0, 0 to 1, 0, and you can see all of them. And some of them is more probable, and you can see more error counts for them. But you can check the paper for more detail. But now we want to design mechanisms, essentially, to reduce these issues. Let's first start with retention-aware error management. So there are a couple of solutions to retention errors. Essentially, you need to refresh periodically, like what you're also doing in DRAM. So you refresh DRAM. And then you need to change the period based on the PE cycle wear out, meaning that once in the beginning, once your PE cycle is low, you don't need to refresh that frequent. But once you have larger PE cycles, you want to refresh more frequently in order to avoid errors. And then you can use a combination of in-place and remapping-based refresh. We're going to see what are these. But essentially, the way that you can refresh, one way is just remap. So you have a page, and you want to refresh that page. You just remap this page to another free page. It's very similar to rewrite it to somewhere else, basically. But there are also ways to do that in-place refresh, which we're going to see. But in-place refresh comes at the price of reliability issues as well. So our key observations are retention errors are the dominant source of errors that we already discussed it, and retention errors can be corrected by refreshing each flash page periodically. And our key idea is that periodically read each flash page, correct its errors using a weak ECC, and then either remap it to a new physical page or reprogram it in place. So this reprogram in place is considered as in-place refresh. And this is important that we should do it before the page accumulates more errors than ECC correctable. Specifically here, we are using weaker ECC. So you need to do this refreshing soon enough before that page accumulates a lot of errors. And there can be optimization, like you can adapt refresh rate to endure the PE cycles. Okay, so how to refresh? As we discussed, remap, reprogram, or hybrid. And as you can guess, we are doing the hybrid. And when to refresh, it can be fixed period or adaptive period, which again, adaptive is better, of course. So in order to do in-place reprogramming is not really magic. So you know that because of retention error, these basically distribution windows, they just move to the left, shifting to the left. And then you just need to apply ISPP to just push it back to the right, essentially. So that can provide in-place update. Sorry, in-place reprogramming or in-place refresh. People have used this idea also to provide in-place update in flash memory. But that's not very easy to implement, and that also comes at the price of some errors. For example, they consider that they are using TLC NAND flash memory, but they only consider that they use only the 4 initial step of that. Like they have TLC, but they only use 4 steps of that. And when they want to move to another, like they want to reprogram it, they can just, again, increase the threshold voltage, and they move to another 4 step. And with that, they can control more, essentially. And then they can reprogram. But the issue is that with those works, and also this work, like this way of doing is about a programming effect that we discuss about. We need to obey the order of programming. So once you program thing, you need to go to the next item. You shouldn't really reprogram the previous one. And doing that, actually reprogramming and doing programming at a different order can cause errors, essentially. And we're going to also see about when we look into programming interference. So yeah, so with good things here is that we don't need to do remap, which is good, but as a cons increases the occurrence of program errors because you're doing that in place, and that can cause program interference errors to other pages. Any question about this technique? Okay, good. So here is our result for normalized flash memory lifetime. And you can see that adaptive FCR provides quite good lifetime compared to other works. And interestingly is that with basically simpler, let me find a good point to show you the trade-off nicely. Yeah, so with this one. So with this adaptive FCR, we could provide the normalized lifetime of 1K BCH code, similar to the baseline that uses, actually no, because baseline is actually quite poor. So forget what I wanted to say. I wanted to show the trade-off that essentially by using this intelligent technique, you can use much simpler code while providing the the lifetime of the stronger codes. But we don't have a good point here to show that. I'm going to show it later. Okay, and for energy overhead, we showed some overhead depending on the reference interval, like how frequently you do it. Of course, you can you can increase energy overhead. Remapping based refresh, has larger overhead, of course, but hybrid refresh can reduce it. But if you do it every day, like the overhead is around basically 5.5%. With adaptive rate refresh, the overhead can be less than 1.8% until daily refresh is triggered. You can check this paper, flash correct and refresh, if you are interested for more detail. Okay, any question? Now we can get to the next topic, which is that dry fig actually caused me. So the next one is threshold voltage and program interference analysis. So we're going to ask some key question here: that how does threshold voltage distribution of different program states change over flash lifetime? And can we model it accurately and predict the VTH changes? So we want to, basically the goal is to model and predict threshold voltage. Because once you have the nice model for VTH, hopefully you can also predict your reference voltage nicely. And that's the key in order to improve both actual reliability and performance. Remember that when you access your flash memory and your ECC fails, you need to retry, right? With another reference voltage. So once you have a nice model of VTH changes, you can actually predict or estimate your reference voltages nicely, and then you can access your flash memory better. That can provide better reliability and also better performance. So here are results from real experiment, actually, that you can see how these basically window is moving through the, and it's not also moving, like shifting to the left, is also widening, as you can see. So after P cycles. So VTH distribution can be modeled with, that's what we showed, that it can be modeled with 95% accuracy as a Gaussian distribution with additive white noise. And also distortion in VTH over P cycles can be modeled and predicted as an exponential function of P cycles. You can read the paper for more detail, but that's the way we model it. But later on, we also observed that when we use flash memories that they are basically more dense, like they have lower scale, then actually Gaussian does not provide very good estimation. Like here is a good example. Like you can see that for 20 kp cycles, these dots are actually real measurements. And this, like exactly in dashed line is the basically our Gaussian model prediction. And you can see that our real measurement was like this. And then at some point, for some reason, we should go to this line. But Gaussian doesn't really understand and just follow the same thing here. And we show that using other modeling, like students T-based model. I don't know what is exactly actually. This is a student's T model. You can read the paper for that. But that can actually, follow the basically our actual results better. So better modeling needed when you, for example, use more dense flash memories. And here also the results, like Gaussian, the average error is 2.6%. Normal Laplace and students T, they provide almost the same average. Like Laplace is even better. But the good thing is that, students T is simpler to implement. So for Laplace, you need to, add more overhead. So that's why students T sounds like a good trade-off among these techniques. But you can read the paper for more detail. The next item is program interference errors. So when a cell is being programmed, voltage level of a neighboring cell changes due to parasitic capacitance coupling and can change the data value stored. It can actually remind you RowHammer thing, right? That when you, but this is about programming. So we call it a program interference error, and that causes near cells to have errors. And it's also important that even though we show that retention errors are dominant, but once retention errors are minimized using all these techniques, then we need to make sure that we are also fixing other errors. Okay, this is a reminder about how this two-step MLC programming works that we already discussed. But now let's take a look at these basics of program interference. So you have this poor victim cell, and there are several actually cells surrounding over this victim cell. And each of these cells can have some delta V XY, delta VY. Basically delta, some variation in the voltage of them once you program them. So fortunately, there is no actually, because of the way that we are making flash memory, there is no interference from the lower level to the top layer. And that's why actually we have this sequence in programming. We always want to program in a sequence from top to down, so that there is no really program interface from this bottom to top. So we have only these surrounding basically cells that they can cause program interference. There has been work on a traditional model for victim cell threshold voltage change, but these models are not accurate. And also you need some knowledge like coupling capacitors, which is not easy to get, essentially. So the goal in this work is that to develop a new, more accurate and easier to implement model for program interference. And the idea is that we want to empirically characterize and model the effect of neighbor cell VTH change on the VTH of the victim cell. And then we want to fit neighbor voltage threshold change to a linear regression model and find the coefficients of the model via empirical measurement. So that's the model that we come up. And you can see that these are can be measured, like this delta V and delta, this also V voltage here, these can be measured. And there are also some coefficient here that you need to set them through this regression model learning. Yeah, you can check the paper for more detail about it, but essentially we use this model and we trained it. And then with that, you can basically predict the threshold voltage change of the victim cell. So we made this very good observation, interesting observation here, that immediately above cell interference is dominant. You can actually see the effect of different neighboring cells on the victim cell. Like the immediately above cell interference is dominant. And then immediately diagonal neighbor is the second dominant. And then far neighbor cells interference also exists, so you cannot ignore them. Yes. Sorry, I couldn't follow the.
Is there any other reason to?
At least is the only reason that I know, but there might be. Maybe Rakesh knows. by stripe, but you're losing capacity, right? Like you program a row and then you leave a few rows and then you write to like row 4, for example, and then you can, and then what you do?
So after you've done all of them,
but then row 1 will have some, when you program row 1, it can have some inference to row 4, for example. I mean, no, the row 0. Yeah. Yeah, also this is in, our observation that victim cells VTH has negative effect on interference, meaning that if you don't have, if you have a higher VTH, your cell will stay stronger with that interference. Okay, so that's about it. So that's why we model it and we design this model, and you can see the accuracy result here. These are the measured before interference, and Y is the measured after interference. So ideally, there should be no, if there is no interference, things should be like aligned, right? Like you need to have a basically this line that X equals to Y. But because of the interference, we have you know, some of these errors. And then the good thing is that we can, with our model, we can actually predict it nicely. And our model corrects for the VTH shift by 96.8% accuracy, which is quite good. Question? This is the paper, ICCD paper, that you can check for more detail. But now we want to see how we can use that for read reference voltage prediction. So once you predict and model threshold voltage, now you can use it to basically set your read reference voltage better. So the question is that what can we do with this model? Our goal is to mitigate the effects of program interference caused by voltage shift. So yeah, the optimum read reference for flash memory. That's the idea that we need. So after some time, you have this, you know, this window of basically threshold voltage that they have some collision. So if you for reference voltage, if you set it like here, you're gonna have basically with this integral, you're gonna see that you have less capacity, right? Less area. And that can minimize the error, which is good. But if you set your threshold voltage here, you're going to have longer, larger errors, and that's not good. So ideally, there exists an optimal read reference voltage. Later on, we're going to see that this optimal read reference voltage actually also depends on every cell. But here we are looking at the flash page, you know, at the high granularity, or let's say at the flash, like the block. But you can also do more fine-grained study that we're going to also see. But essentially, there should be one optimal read reference voltage, and we want to predict that with our model to see, and then access our flash memory using that optimal read. Okay, so yeah, these are also what you know. Yeah, here you can see the effect of read reference voltage prediction. The red line is that there is no read reference voltage prediction, and you access your flash memory. So you have higher row bit error rate, but with read reference voltage prediction, you can reduce error rate, meaning that you can actually also reduce you can make your ECC simpler. Yeah, this is actually one of the points I wanted to make in the past. Like with 32K bit BCH code, your acceptable bit error rate is 2 times 10 to the power minus 3. So with that ECC capability, you can increase the lifetime by 30% if you use this technique, essentially. Of course, if you use a stronger BCH code, you can actually also provide higher lifetime. But this is very interesting to see that using the same ACC code and such an intelligent mechanism, you can actually extend your lifetime. And that's good. Yes. Yes. You mean to every cell or every page? Yeah. Yeah, we actually, that's the way we do that, you know. Once flash controller wants to access, to do the read, basically to send a read command, it should also specify read reference voltage. And it can, flash controller can, you know, can dictate different reference voltages. So the thing is that you access your flash memory and you read erroneous, and you cannot fix it. So you want to retry your access. You need to change the reference voltage. But how are you going to change it? You know, if you're going to just reduce it a bit and then access, then that might not be good enough, right? So the idea is that with this kind of technique, you can predict reference voltage better. So such that you can access your flash memory and read well at the first time. But even if you also cannot get the result at the first time, the second attempt can be much better, can be better. So that's the main reason that it also provides better performance, because you're reducing the number of read retries, essentially. Yes. And that's the problem that I said here. You know, we are using this optimal read reference voltage, considering the whole page. But you can actually be a bit more, let's say, fine-grained and consider every cell. I'm going to show later. Okay, question. Yeah, if you want to also learn more about this topic, you can check our later works on this line of modeling. I also showed this non-Gaussian VTH distribution that, you know, with better modeling, we could provide better, you know, estimation, and such that with better estimation, you can also better tune the reference voltage. These are, we already discussed. And yeah, so with this online read reference voltage prediction, this is like 3 plots. We have P, you know, increasing P cycles. And we have different like model, like the actual device, like you get results, and Gaussian model that you use, you know, your Gaussian, your distribution, normal Laplace and student's T. And this is like the model optimal read reference voltage. So the actual read reference voltage is the one that you get from experiment. You know, from experiment, you get to that. These are the basically optimal read reference voltage. And other points are the points that you estimate that using your models. And you can see that some of these models are quite off, like Gaussian, you know, doesn't really, you know, nicely map to the actual one. But the student's T and the normal Laplace, they are actually quite much better. And that's why we show that basically it's better to use student's T model, for example. This is also effect of row bit error rate of read reference V prediction. So once you better predict, you can actually also, you know, follow the same thing that you can get from actual optimal voltage. But again, you can see that the Gaussian is not really well. I mean, sometimes it doesn't map well, and other models are better. But you need to check the paper for more detail about it. Question? Good. Okay. Good. You are going fast enough. Another interesting topic is actually neighbor-assisted error correction. Essentially, you want to use the data stored in your neighbor cells to correct your errors. This topic is actually quite exciting to me always. So the goal is that we want to develop a better error correction mechanism for cases where ECC fails to correct a page. These are our observations so far. We know that immediate neighbor cell has the most effect on the victim cell when programmed. We showed that, right? And we know that a single set of read reference voltage is used to determine the value of the victim cell. The set of read reference voltages is determined based on the overall threshold voltage distribution of all cells in flash memory. So that's, when we want to get that optimum threshold, like optimum reference voltage, we set it based on the overall threshold voltage distribution of all cells. But we want to now do it in more fine-grained, essentially. The thing is that the threshold voltage distribution of cells with different value immediate neighbor cells are significantly different. That's our observation in this work. Depending on basically the value of your neighboring cells, you're going to get different distribution for your threshold voltage. And if we know the value of the immediate neighbor, we can find a more accurate set of read reference voltages based on the conditional threshold voltage distribution. Now, the distribution is conditional. You're saying that if my neighboring cell value is, for example, 1, 0, now my distribution is this, Then I can have a different distribution. For example, if my neighboring cell is 1, 1, for example. So you can actually make all these basically distributions. So here is an example. You have aggressor word line with all these values, and there is also this victim word line. So the victim word line after MSB page of aggressor word line or program is like this. So this is the overall distribution. But distribution for these cells that they have, the neighboring value is 1, 1 is like this. And for 0 and 0 is like the yellow one, 1, 0 is the green one, and also that's the purple one. So now you can actually have different reference voltage. Instead of having only one reference voltage, you can, based on the basically the neighboring value, like the conditional reading, you can set different reference voltages. Right? And with that, actually, you can hopefully read without any errors. Look here, when you read, even with this optimal reference voltage, you're going to have some errors. And you should hope for ECC correction capability, to fix these errors. But using this conditional reading, you can actually get rid of everything, all the errors, hopefully. And that's really good. But the price is at the price of basically much more costly reading. So we apply this technique only when basically, these are the same thing. Like you can see that the bit error rate for overall, using the overall reference voltage is around like 3 times 10 to the power minus 4. But when you use this conditional reference voltage managing, you can get to much lower bit error rate. So that shows actually the power of this technique. But as I said, this is quite costly because you need to apply different reference voltages. I mean, reading from MLC is costly, but now you need to come up with different also reference voltages and access your basically flash page with different reference voltages. So the idea is that we do that only when ECC fails. So we access our flash memory, we read with the optimum basically reference voltage that we come up with our models. If ECC succeeds, then everything is good. But if ECC fails, we try to read the immediate neighbor page. So we read that. And then we check we try to reread the page using the neighboring values that we have. And then we can apply ECC. So this is the flowchart of this technique. Basically, for read requests, we read the page. If ECC is correct, then we send data out. If no, we need to read LSB and MSB neighbors. And we read the page from flash using the next set of local optimum read reference voltages, essentially. So you have a set of read reference voltages, right? Assuming the value of your neighboring cells. And then you use that, and hopefully you can correct the page. If ECC is correct, then you're done. If not, you can actually continue that using other local optimum voltage. Like we had different reference voltages here, right? Depending on the neighboring values. If it's 1, 1, we have one reference voltage. If it's 1, 0, another, 0, 0, another, and 0, 1, another. So you can actually apply all these reference voltages as much as needed. So you first access with the overall, you read. If ECC works out, then you're done. If not, you need to apply basically reread from that flash memory using, for example, the reference voltage of which is basically corresponding to this 1, 1 value. You read, and then hopefully you can fix the errors. If not, you should continue with reading also with 1, 0, 0, 0, and 0, 1. And at some point, if nothing work out, then you're done. I mean, and you're not hopefully done, but your flash memory is dead. So you just propagate error. Yes. Yes, that's why. Yes, of course. That's with that assumption. Yeah, of course. If you read that neighboring also, you can that has error, then error can be propagated. Yeah, but this is actually quite exciting idea that you can use your neighbor to fix the errors. And we call this technique as NAC, neighbor assisted correction. And with that, you can actually have some lifetime extension. So this is your ECC capable of correcting 4 bits per 1 kilobyte. So this is like ECC power that we have. So you can see that without NAC, this is the lifetime. So after this, you cannot really correct things. But with NAC that consider all different values of neighboring cells, like 1, 1, 0, 1, all the patterns, you can extend the lifetime by 39%, essentially. Yeah, I'm not sure why is it. Oh yeah, 33% lifetime improvement at no performance loss. But because once you want to apply this stage 3, you may have some performance loss. Okay, and here are also the result for performance. The takeaway here is that we don't have performance loss within nominal lifetime and with reasonable ECC fail rates. Of course, at some point when your PE cycle is quite high and PCC, like the probability of ECC fail is high, like 33%, then yes, you're going to have a lot of performance overhead. But that is not the, I mean, probably your system is already done, and you shouldn't really use that system with that 33% ECC fail. This is really high. Okay, so you can also read the paper for more detail. Question? Okay, let me also cover this paper and then we can take another break. Redistrib errors in flash memory. We discussed about this issue that we have in other memories, that all scaled memories are prone to redistrib errors. For DRAM, we know RowHammer, RowPress, for example. In SRAM, we also have this. In hard disk, also, we have this adjacent track interference. If you're interested, you can check for that. But in NAND flash memory, also, we have this issue. The problem is that once you want to read, you need to apply a reference voltage to one page, and to other pages, you need to apply VPass. And you know that VPass is high enough to make all these cells in that page, operate as a resistor, basically as a switch, because no matter it is program or arrays, so VPass should be higher than threshold voltage, essentially. Okay. So yeah, these are background that you know already. You apply VPass, and then you can read. So here is the basically I want to show the problem with some basically with this example here. So you want to read page 2, you apply a reference voltage to page 2 and repass to other pages. And you can read basically well. So you have the results 0011, and that's the correct values for page 2. So far, so good. But the problem is that if you do this repeatedly, so you want to repeatedly read, for example, page 3 or any page other than page 2, basically, then you're going to cause some weak programming effect. Because once you apply VPass, that VPass is actually high. It's not as high as programming voltage, but it is a bit high, and that can cause some weak programming effect. So essentially, applying VPass can increase the threshold voltage of the cells a little bit. And at some point, if you do it repeatedly, like hammer it, so you're hammering this basically this word line by accessing it a lot. But so that VPass will increase the threshold voltage of other basically other pages. So this VPass can, for example, this 2.4 volt is the threshold voltage. So now because of VPass, it increased, for example, to 2.6. Now you want to read. So you apply reference voltage. And since the threshold voltage of this cell has been increased a little bit, now it works as an open switch, and you read 0, which is wrong. So that's the problem of weak programming that causes you read incorrectly. Hopefully, you can fix these errors by ECC, but you cannot rely on your ECC capability all the time, essentially. So we wanted to also reduce the effect of this read disturbance error. We did some characterization, and we made very interesting observation. Like slightly lowering the VPass greatly reduces read disturb errors. That's very interesting. I will show you a plot for that. And there are some flash cells are more prone to read disturb. So for first technique that is based on the first characterization result is that we mitigate read disturb errors online by tuning VPass dynamically to find and applies a lower VPass per block. And then with that, flash memory lifetime improves by 21%. And the second technique, we recover after failure to prevent data loss. So after some time, your flash memory, after applying all this technique, you cannot read correctly from your flash memory. So your flash memory is considered as a dead device, essentially. So then you can actually spend a lot of time, try to recover, and hopefully get your data nicely. So the good thing is that for that recovery, you have time. You don't need to do it like on the critical path. You can do it offline. And because of that, you can actually apply much more sophisticated technique. And you're going to see that the technique that we used here is actually quite complicated. But that can recover some errors. And we show that basically this read disturb oriented error recovery selectively corrects cells more susceptible to read disturber errors. And that reduced row bit error rate by up to 36%. So with this recovering, we reduce row bit error rate by up to 36%. And then now your error rate is actually hopefully in the range that ECC can fix the rest. So now you can actually put your flash memory back to the device and read from it. And then you can hope that ECC fix the rest of errors, essentially. Okay, so this is observation that I talk about it. So here you can see we have different VPass, like 100%, meaning that you applied your nominal VPass. And then we have different, like slightly reduced VPass, like by 99%, 98 to 94%. And the x-axis is the read disturb count, like how much you hammer, essentially, your flash memory, and this is row bit error rate. So you can see that by slightly reducing VPass, you can significantly tolerate much more read disturb count, essentially. So for example, with, and this is the normalized row bit error rate that you can tolerate. It's not actually normalized, it's 1 times 10 to the power minus 3. So this is your row bit error rate that can be corrected by your ECC technique. Meaning that if you exceed this line, you should consider that basically your your flash memory is dead because you cannot read correctly from it. So yeah, by reducing VPass, for example, from 100% to 94%, only 6% reduction, you can significantly increase the lifetime. From something around 5 times 10 to the power 4 to something around 10 to the power 8. And here also another result that you can see 3 orders of magnitude, like better, visualization of the previous thing. Like by reducing the VPass by 6%, you can provide 3 orders of magnitude higher, basically, lifetime. So this is really good. So our mitigation is that we want to tune VPass. Of course, there is a trade-off here that when you lower VPass, you allows more read disturbers. So you can actually tolerate more read disturbs, which is good. But that can also induce more read errors because now you reduce VPass. And since your, so the reason that VPass is set high is because of some guard band, essentially. So because of the process variation, they consider that VPass should be high enough such that, no matter of cell position, like the characterization of that cell, it will work as the resistors, essentially. But once you reduce your VPass, so you are eating up through the guard band, essentially. So now there can be some cells that they may not be turned on if you apply that lowered VPass, and that can cause issue. Here is an example. Like this cell, you can see that the threshold voltage is 4.8. If you apply VPass 4.9, things are bright, and you can read nicely. But if you reduce VPass to, for example, 4.7, then you have issue because this cell won't act as a resistor, essentially. And that can cause errors. Is that clear now? So now you can see the trade-off here. Reducing VPass is good in order to reduce read disturbance error, but it can also cause some other errors. So our idea here is that we want to utilize the unused ECC capability. So here in the x-axis, you can see the retention, like the number of days. And for each day, like when your device is actually quite early, like quite young, your row bit error rate is much lower than your ECC capability. So you have quite unused ECC capability, meaning that at this, if you are in the first day, you can apply much lower VPass. You can reduce VPass a lot because if some errors happen through that read, hopefully your ECC can correct them because your ECC capability is quite high. But once you are in this position, for example, then you cannot reduce your VPass much. So that's the idea here. So ECC provision for high retention age, as you can see, and unused ECC capability can be used to fix read errors. And unused ECC capability decreases over retention age, as you can see here. So we want to dynamically adjust VPass so that read errors fully utilize the unused ECC capability. So what we are doing is that we conservatively, so that's what is happening today, that people conservatively set VPass to high voltage, and that can accumulate more read disturb errors at the end of each refresh interval. But it provides no read errors. Our idea is that we want to dynamically adjust VPass to unused ECC capability, and that can minimize read disturbers error, but it comes at some cost. So you need to control read errors to be tolerable by ECC, and that's the key. If read errors exceed ECC capability, then you need to read again with the higher VPass to correct read errors. So that's the technique. How we tune it, we perform once for each block every day. We estimate unused ECC capability using retention age. And then we aggressively reduce VPass until read errors exceeds ECC capability. And then we gradually increase VPass until read error becomes just less than ECC capability. It's quite simple, right? And with that, you can tune it. So we tested on 19 real workloads, and we assume 7-day refresh periods with a similar methodology as before to determine acceptable VPass reduction. The overhead for a 512 gigabyte flash drive is around 128 kilobyte storage overhead per block to set VPass and worst case page. And also we need to do this 24 second per day average VPass tuning overhead, which is, can be considered as acceptable overhead. So here you can see the result at average the lifetime improvement is 21% by VPass tuning. And this is the baseline, but VPass tuning, essentially you can tolerate much more read disturbers. Okay. Yeah, the second topic is a bit more complicated. Let's talk about it after the break. Let's have a 10-minute break until 3:21, and then we will continue. I know. Who is the first to scribe? Oh, how come? I see. Yeah, micro conference basically screwed up our schedule. Okay, shall we continue? So this is another point of it that we use actually to recover. It's actually quite interesting. There are some cells that they are disturb prone, and there are some cells that they are resistant. So they don't really move much. Here is an example. Like we show, like by having these read disturb errors, like when you apply VPass and then the VTH change, these cells that they are disturb resistant, they don't move much. However, disturb prone, they move much. So now if you want to be more accurate, you should actually also differentiate across these cells. But the point is that this is not really easy to do, and it's actually quite costly and time consuming. And that's why we are doing that for recovery, and we are doing the operation offline. Here is the second observation, that some flash cells are more prone to read disturb, as we also discussed. You can see that in each of the state that we have, like erase state, there can be some cells that they are resistant and some cells that they are prone to disturb. And also the same thing for the program state. Once you apply these basically read disturb errors, things will just shift to the right, but not every cell shifts similar, basically, you know. Some of them shift more, like prone, actually, they shift a lot. And then resistance, they don't shift much. So now the issue is that if you actually apply optimal voltage, you're gonna read wrongly, essentially. So you can see that because it's actually shift, right? So the distribution has been shift. Your optimal threshold, like the optimal reference voltage needs to be here, essentially, right? But now you're reading wrongly because of these cells that they moved. Some of them, they move more, some of them less. For example, this one stay in the correct, actually, like the situation. But the problem is that because now it has conflict with the ER state, if you use that optimal voltage, you will read it as 0. And that's wrong. So that's the idea. If you want to understand, if you want to fix all these errors, you should understand the difference between prone and resistance, and then try to tune your reference voltage based on that. So this mechanism is actually quite costly, and that's why we trigger it by an uncorrectable flash error. So once you have an error from flash that you cannot correct it, you back up all valid data in the faulty block, like all valid data that you have in that faulty block, not back up everything in a faulty block. So you back up all valid data in the faulty block, and then disturb the faulty page 100K times or more than that. And then you need to compare the threshold voltage before and after read disturb. Essentially, with this mechanism, we want to see what are the cells they are susceptible to flash errors. Basically, what are the cells that they are disturb prone, and what are the cells that they are disturb resistant. And those are that disturb prone, they have lower threshold voltage state. So cells with, so that's the idea, basically, you know, that we get here. Cells with more threshold voltage shift are disturb prone, meaning that their threshold state should be much lower than what we already have. So that gives you an idea. If you want to correct it, you need to consider that, okay, these cells, since they are disturb prone, they have moved a lot. meaning that the initial state is actually much lower. So that's the way that we consider. And cells with less threshold shift are disturb resistance, meaning that their threshold state should be higher. So with that, we can reduce total error count by up to 36% at 1 million read disturbs, and ECC can be used to correct the remaining errors. So if you don't do any recovery, you're gonna see that your device will be basically this is gonna be your, read raw bit error rate. But with this RDR that you do, like this offline, we can increase the lifetime much more. We can, of course, read the paper for more detail. But now I want to talk about retention error handling, essentially. We talk about retention error a lot from the reliability perspective, but now we want to see how we can, basically, we want to look into this area from the performance perspective. Because as we discussed, retention error cause performance degradation. So we did characterization for retention loss in real NAND chip. And then we want to optimize read performance for all data. And then we want to recover all data after failure. This recovery, again, is very similar to also recovery that we have done for the previous work that I showed you. Is actually happening also offline. But the optimization is happening online. This is this very interesting slide report from one of the Samsung SSD. I also talked about it yesterday. It's actually an unfortunate tale about Samsung SSDs. It's not only about Samsung. I mean, all SSDs have that problem because of read performance degradation. So you can see that reading old files is consistently slower than normal, as slow as 30 megabytes per second. Whereas basically newly written files, you can read them with 500 megabytes per second. So essentially you can observe one order of magnitude overall, less throughput when your device is old. Your device does not need to be old, but your data is old. So there are some data that you program to your SSD, and then you don't basically update them for a while. So accessing those data, like old files, are much slower compared to newly written files. So that's a very interesting point. So why is old data slower? Because of retention loss. And so you know that because of this retention loss, you can have retention error. And that's one dominant source of flash memory errors that we showed. But the side effect that we want to focus on this work is that longer read latency. And why is that? Because essentially, you need to apply. So the first read attempts fail, So with this, after retention loss, you're going to get to this kind of curve distribution. And then your first read attempts might fail because of raw bit errors larger than ECC correctable errors. Then you need to you need to basically adjust your reference voltage and retry your read. This is the read-retry process. And that can essentially increase read latency. So hopefully with that, with second attempt or third attempt or sometimes fourth and fifth attempts, or maybe more, you can get to fewer raw bit errors, which you can correct them with ECC. So why is all data slower? As a summary, because of retention loss, you leak charge over time, and that generates retention errors. That calls for read-retry process, and that is cause longer read latency, essentially. So we want to optimize it by doing optimize the read performance for all data, and that's with optimal read reference voltage. So we want to basically estimate what is the read reference voltage should be, and hopefully access our flash chip with that optimal voltage, such that you can read at the first attempt. The optimal changes over time. Voltage changes over time due to retention loss. You can see. So now optimal read reference voltage here, but after some time might be here, for example. So you need to actually do it frequently. But luckily, optimum change is gradual and also unidirectional. So with this retention error, everything is unidirectional. Things are going to the left. we show that actually the threshold voltage can also shift to the right because of do you remember? Because of the right interference problem, right? Because of the right interference problem, you can shift things to the right. But with only for the retention error, if you are basically concerned about it, things will just go to the left. And that's a very good thing, because that can make your model basically easier. So then we get to this technique, retention optimized reading, ROR. That has two components. The first is online pre-optimization algorithm that learns and records optimum voltage, and then performs in the background once every day. And then we have simpler read-retry technique that if recorded optimum is out of the date, we need to read-retry with the lower voltage, essentially. So you have some recorded optimal voltage, and you're going to use that in order to access your flash memory. But sometimes you realize that you cannot rely on your optimal voltage because it's out of date, because you don't update optimal voltage all the time. You update it like once every day, in order to reduce the cost, essentially. So if your recorded OPT or optimal voltage, optimal, there is a clear difference between optimal and optimal. So if recorded optimal voltage is out of the date, you need to read-retry with lower voltage, essentially. Okay, and this is a technique that we triggered periodically per day, and find and record an optimal as per block for prediction. And that can improve read-retry technique, as you can see. So with this technique, we can reduce the read-retry count by 30%. And the latency for ECC decoding also has been reduced by 90%. I mean, by 10%, basically. And the total read latency now is 29%. So you can see that we significantly improve performance for old files, essentially. For new files, you don't really have that much issue. But for old files, you have a lot of latency issue, because you need to retry the reads a lot of times. So with this technique, we can learn optimal voltage periodically, and then we can minimize read-retry and row bit error rate, and we can hopefully get to shorter read latency. Any question? Sorry? Yes. No, actually, I cannot say, cannot pick point, that this technique, for example, has been implemented. But I think that general, I mean, many of these works and other works that other people have done in this research in this area have been implemented in flash controller and SSD controller. And that's a very interesting point that you bring it up. Like, essentially, flash memory was kind of emerging memory technology in the beginning, and no one was really excited, or let's say, I mean, no one is actually a bit quite exaggerated. There has been some people that they were quite like optimistic and they were looking futuristic, but many people actually were quite pessimistic about this architecture. But a lot of people have done, research on it to make this flash memory work. And now we can see the result of that. So you just use your SSD and you don't really, experience many of these errors, or still you can actually experience some slow access. It actually happened to me as well. So when I want also to open the files that I have that they are quite old, I can see that those files are slower. I mean, you can also check if you have the records. So for example, I have some lectures or videos that they are for 10 years ago in my laptop. And those, when I want to open them, it takes more time. And you can really, sometimes you can actually feel it. So this is quite interesting. That's also the case. And my laptop is working for 10 years. I mean, that was actually a bit exaggeration. My laptop age is 8 years. So. Okay. Okay, so now we discussed about optimization. Now we want to recover. So there are some old data that they fail, and you cannot fix the errors of them, and now you want to recover them. Again, we use this idea that we also have shown in the past. We use it for read disturb error. So there are some cells that they are low leaking cells. You know, you know, the speed that they lose retention is actually quite, much slower. And there are some cells that they are fast leaking cells. So if you know them, you can actually better correct things, essentially. So here is also an example that you have. And then after some time, you can see that these fast leaking cells, they go, they reduce charge much faster. And they can go to the, the erase state, essentially, at some point. And there are also some slower states that they don't move much. So now you can see that you can get to some errors. If you use this, for example, optimal reference voltage, because of these fast leaking cells, this one you're gonna read it as 1, even though you should read it as 0. Or for example, because of these slow leaking things, this one you're gonna read it as 0, even though you should read it as 1, essentially. So once you have this data, you can differentiate across these cells, and then you can correct errors more. And that's the way we are handling it. So the key idea is that we guess original state of the cell from its leakage speed property. So we do some experiment to understand how fast our cells are leaking charge. And then based on that speed, we can guess the original state of the cell. Identify risky cells, and then we identify fast, slow leaking cells, and then we guess original state, as I said. And this is the evaluation, essentially. So you program with random data. After 28 days, you can detect some failure, and then you need to back up data. And then we need to spend like 12 additional days in order to recover data. As you can see, this process is actually quite slow. But the good thing is that you are doing it offline, and for recovery, and the outcome is good, because without this technique, without this recovery, your flash memory is dead. But now you spend 12 additional days and you make it, workable. So our expectation was to eliminate 50% of row bit errors, and hopefully ECC can correct remaining errors, essentially. Question? Yes. Yes. Exactly, but that's happening offline, basically, right? Yeah. Yeah, that's also a conclusion that I showed. I discussed about retention optimized reading, ROR, that can provide 71% shorter read latency, and retention failure recovery that can recover data after failure, which is good. You can check this paper for more detail. Any question? So the thing is that you read from flash memory, you see some errors, and you cannot fix it, okay? And then you try to guess what's the issue. So you can see that, okay, this is my, so this is the bit vector that I read, and without knowing anything, you are just basically blindly, relying on ECC correction, right? But once you know this issue, that that, okay, like position 5 in that bit vector is a leaky cell, for example. Probably that bit can be, for example, 1, should not be 0, right? So you just flip that bit and then apply ECC. And hopefully ECC can fix the thing. That's it. That's the idea, essentially. Question? Check. Okay. So let me also show you some larger scale feed analysis. We have done also a similar study for DRAM that we have discussed, I guess, in one of the lecture. But now I want to show this study we have done with Facebook, and like we wanted to see how SSD error, SSD error analysis of Facebook system essentially. So we observed that a few SSDs cause most errors. So you can see from this picture that like there are some SSDs that cause much more errors, and that's also expected. I mean, that's also the case for DRAM modules. There are some DRAM modules that they are more error prone essentially. So we did our study. This is the summary that we consider SSD life cycle. We also consider the effect of read disturbance, temperature, and access pattern dependence. I'm not going to cover detail of this study. You can read the paper for more detail, but I will just give you some insight about it. And this early detection life cycle period that distinct from hard disk drive life cycle. I'm going to show some result about it, but again, you can check the paper for more detail. Are you guys familiar with bathtub curve? What is it? Yeah. Yeah, this is the, and this doesn't need to be actually related to electronics and devices. It can be also related to cars, for example. You know, there are some products from manufacturer that they are not tested just enough, you know, because of the, you know, every time you test, you have a coverage essentially. So some of your devices, when they are used in the domain, they're gonna fail very fast because you didn't test them enough, just enough. But those devices that they survive for some time, luckily they will also survive much more because they don't really have, you know, serious, let's say, failure issues. So that's why we have a quite high failure rate in the beginning, but at some point we don't have much. But then we get to the wear out situation of the device, that our device is aged, and then our failure rate also again increases. So you can see this early failure period, useful life period, and wear out period. So our question here is that do SSDs display similar life cycle periods? We wanted to test it. We didn't get to this exactly same basically curve, partly because we use a metric which is time independent. Like we didn't use here like the usage depending on also the time, but we also use here is the number of used data written to flash to examine SSD life cycle. So here are the results, like how much data. You can see that we get to something similar to bathtub curve. Like this is the early failure period. And this part is kind of useful life period. And now here is kind of wear out period that we observed from our experiment. But also we get this early detection period that failure rate in the beginning was low, but then jump high. So this is actually quite exciting, but you can read the paper for more detail about it. We also did this analysis on temperature. So SSDs, they have temperature sensor, so you can actually profile temperature. There are some SSDs that you can see that when because of the load of them, temperature increases, and then your SSD failure rate also increase. So that's not good. But there are also some SSDs that they do some throttling technique or shutdown. When the temperature is high, SSD throttle itself or shut down. So that to control the temperature. And with those SSDs, you can see that basically failure rate doesn't really increase much with the temperature increase. So of course, throttling comes at the price of performance, but once your error rate is high, this might be a good decision, you know? Okay, so, and again, even though we show that read disturbance errors is quite important in all the research that we have done, but we do not observe effect of read disturbance in this study. And the reason is that we did this study at the software level. So read disturbance is actually happening most of the time at the flash layer, like from when you read from flash memory. And most of the time, flash controller fix all these errors. And then data is actually sent out of the SSD. sometimes your SSD cannot actually correct the data internally and then send it to the OS, but you also have some error correction capability at the OS level. For example, using RAID, which is redundant array of independent disks, right? Neva. So RAID is actually one of the technique that people have developed in order to provide reliability across several disks. So with that RAID, you can also fix some errors again at the OS level. So basically, you have a lot of different error correction capability such that they can hide errors. But so that's partly the reason that we didn't really observe disturbance, read disturbance error at the software layer. And throttling SSD usage helps to mitigate temperature-induced error that we have shown. And for access pattern dependence, we quantify the effect of the page cache and write amplification in the field. Like page cache is the DRAM, internal DRAM buffer that we have inside the SSD, you know about it. And write amplification, we also discussed it, right? Because of the garbage collection, for example, you need to copy things from one block to another block. So that caused a lot of internal writes, which we call it, in the end, adds up to the total number of writes, which is write amplification. So with that, you can have, you know, in the paper, we also quantify the effect of that. You can check and read about it. Any question? So we have done other works. For example, this one is also quite interesting that we, you know, look into vulnerability of MLC NAND flash memory programming. Like this work studied the reliability issues and potentially that people, you know, these reliability issues can be used for security attacks, essentially, which is not really easy because you need to go through a lot of OS stack when you want to access your flash memory. And internally also SSD, there is this mapping table that just map things, you know, differently in the physical. So it's very hard really to understand and try to attack. But this were actually discussed it a lot. And it's actually very nice reading. And I recommend you guys to check, but I don't really have time to go over it. And this will also be discussed already. Okay, okay, we have around 15 minutes and enough more or less to cover also 3D NAND flash memory. So we also have done some works on the 3D NAND flash reliability. As I said, in 3D NAND flash memory, since people, you know, the vendors, they could provide capacity at the third layer and at the 3D layer, so they could reduce, basically they could increase the cell size. And that can provide better reliability. But as we also go into the future, like in order to provide even higher capacity, they also need to reduce the cell size for 3D NAND flash memory as well. And that they are now also experiencing a lot of issues again. I'm gonna discuss a few papers very, very quickly. I'm not gonna go over them in detail. But that's a fundamental issue that we always have. Like when you go from generation N to generation N+1, even though you need to apply a higher, basically ECC, and I mean more powerful SSD. So your ECC limit is higher, such that you can get higher lifetime. But in the end, also your lifetime is decreased. So in order to get the same lifetime, you really need to have quite powerful ECC. I don't know where, but you should be really powerful. But that's the fundamental scaling issue that we have. And one of the reasons that we have done a lot of work in this area to make flash controller more intelligent in order to push the boundaries for ECC limit. So we know that we are bottlenecked by ECC and the cost is actually exponentially increased. So you want to make your flash memory, flash controller more intelligent such that you can, you know, push the boundaries and have better lifetime considering the reasonable, you know, overhead for ECC. This is a slide that we already showed about the planar NAND flash memory and 3D NAND flash memory, and this is the structure that you know, and comparison across 2D and 3D NAND flash memory. So yeah, in this work we discussed 3D NAND flash memory. The problem that we focus on is that 3D NAND error characteristics are not well studied. So that's the main thing that we wanted to learn about 3D NAND flash memory, our goal was to understand and mitigate 3D NAND errors to improve lifetime. And we made several contributions. Like the first contribution is that we characterize real 3D NAND flash chips, and we observe process variation, which is actually quite interesting, like 21 times error rate difference across layers. Now, since you have different layers, you can see that you have process variation across layers, which is also expected, but it's good that we also get it from these numbers. And we also have this early retention loss. I'm going to show a picture, like the plot for that. You're going to see that error rate increases by 10 times after 3 hours. This has not been the case, actually, for the 2D planar NAND flash chips. We're going to see. And another issue, which is retention interference, which we have not observed before in planar NAND. So now the problem is that retention error has some interference on other, flash cells as well. But I'm not going to cover it, and you can read the paper for more detail. The second contribution is that we model row bit error rate and threshold voltage similar to other works. And then we design some mitigation techniques like layer variation ever reading, this one L1 LI rate, which is layer interleaved rate, and REMAR, which is retention model away reading. And overall, we improve flash lifetime by 1.85 times or reduce ECC overhead by 78.9%. So you can get much longer lifetime if you use the same ECC correction, but you can also reduce ECC overhead by 78.9%, and then you can get the same lifetime. And that's very interesting to look into this trade-off all the time. So let's discuss quickly about this observation, like the characterization results. We have process variation across layers, and we report results for that using our system, like real study that we have done. And you can see that, this is the row bit error rate across different layers, and we report errors for LSB and MSB. And you can see 21 times difference across different layers. So we have large row bit error rate variation across layers and also across LSB and MSB pages. So there is this variation that we should consider. And for retention loss phenomena, we got very interesting results. This is a planar NAND, and we know this retention loss, but retention loss in planar NAND is actually happening much, slower. The thing is that for 3D NAND, row bit error rate is much lower, to begin with, but then it accumulates a lot of errors only for 3 hours after it's being written, which is very interesting. So after 3 hours, actually, we have 10 times higher row bit error rate. And after 11 days, we have 10 times more. And after 3 years, we have 10 times more. So the speed actually gets slower as we go to the future, as we use our device. But it's very interesting that we call it this 3 hours, and that's why we call it these early retention errors that we have in the 3D NAND flash memory. So we have this layer-to-layer process variation. We have early retention loss, and we have retention interference. That amount of retention loss correlated with neighbor cells states, which, as I said, you should read the paper for more detail of that. And we design mechanisms for all of them. So we design models. I'm not going to cover models again. The methodology is very similar to what we have done for 2D planar, because overall things are similar. We get to very simple models. Like early retention loss can be modeled as a simple linear function of logarithm of retention time, but take it as a grain of salt, because by going to the future and also using more dense 3D NAND flash memory, things can be changed. But with that 3D NAND flash memory that we have tested, basically we get to these models. So we model it, and here are some results about how effective that model is. And then we wanted to design some mitigation techniques based on that. So the first technique is layer variation ever reading. So we have this layer-to-layer process variation, as we discussed, and the goal is to adjust read reference voltage for each layer. Essentially, we need to have different reference voltage per layer. And the idea is that we need to predict that using our model and get that offset, essentially. And that can reduce row bit error rate on average by 43%. Another interesting technique is that we use layer interleaved RAID. RAID is actually a traditional technique, as I said, redundant array of independent disks. Essentially, you have an array of disks, and you use one of these disks as a redundancy. For example, you have XOR of your data, the whole data on one disk, and you have also other disks. So if one of these disks fail, then hopefully you can get that data from that disk using the other 3 disks, for example. And there are different versions of RAID, like RAID 0, RAID 1, RAID 4, 5, 6, and you can check papers. But here also we use similar idea, but we make a RAID actually across layers, which is actually quite exciting. So we have different layers and word lines. There are some layers that they are more prone to error. For example, this layer number 2, that's what we observe. Layers that they are sandwiched across different layers, they are more prone to error. So group 4 has more errors. So if you group basically chips that they are in that layer, if you group them like this, it's not very intelligent, because once things are basically you have errors, you cannot really fix it, because all data that they have kind of worst case errors, they are grouped together. So you don't want to do that. You want to group things in a way that you have cells that they have worst case, and also the cells that they have best case. So when you group them, hopefully you can recover from errors. So the idea is that we want to group them in a different way. And that hopefully we can basically fix the errors using this RAID. Make sense? And this technique to retention model aware reading. So early retention loss, we have the threshold voltage shifts quickly after programming. And our goal is to adjust read reference voltage based on the retention loss. Our key idea is that to learn and use a retention loss model online, and we design a mechanism to periodically characterize and learn retention loss model online, and we basically model this retention time. And then we predict retention aware V optimal using the model. And that can also reduce bit error rate, row bit error rate on average by 52%. Okay, so you can see the result here. Here is the baseline, and this is our ECC limit. And by applying different techniques, like this red plot is our work, you can extend the lifetime by 85%. And here also you can see that if you want to get the same lifetime as the baseline, you can lower ECC storage overhead by 79%. And this is the summary. Question? Okay, so there is only one more idea that I'd like to also cover. There are also some other slides in the backup that you can check at home. But let me also quickly go over this paper. I just want to give you the idea, which is improving a NAND flash memory lifetime with write hotness aware retention management. I'm going to cover only the executive summary, more or less. So flash memory can achieve 50 times endurance improvement by relaxing retention time using refresh. So we know that, right? By refreshing, you can provide better, basically, endurance. And then the problem is that now the refresh, they come at the price of issues. So frequent refresh consumes the majority of endurance improvements. So you can also guess, right? Especially because you do this ring mapping. So our goal is to reduce refresh overhead to increase flash memory lifetime. Key observation is that refresh is unnecessarily for write hot data. So our key idea of write hotness aware retention management is that we physically partition write hot pages and write cold pages within the flash drive. And we apply different policies like garbage collection, where leveling refresh to each group, meaning that for write hot pages, you don't really need to refresh them much. Yeah, I can see there are some similarities, but yeah. Okay, so yeah, the key results that with the warm without refresh improves lifetime by 3.24%, and warm with adaptive refresh improves lifetime by 12.9%, which is good. So you can actually check the paper, like some of these slides, but you can see that this is the way that we usually have, like cold pages and hot pages are scattered, but we want to physically partition such that we have a hot and cold page, and then we can manage them differently, basically different policies. And that's the idea of this work. Any question? So let me conclude. So these are a summary of the key works that we have done in this line. So of course, I would recommend you guys to check this survey. You can learn a lot from about the flash memory, different mitigation techniques, reliability issues and mitigation techniques. And I already I discussed some of these works in this talk. And this is also another work that we also discussed today about flash vulnerabilities. So check this survey, please. And this is also more up-to-date version of that. And with that, I conclude today's lecture at 4.1. Thank you. So see you next week. Have a nice weekend.